Welcome. So if you're managing a multi-cloud environment, you already know the stakes are just incredibly high. When things break, the pressure is on, right? Today, we're going to build a mental framework, a system to cut right through that chaos and solve those seemingly impossible network issues. Let's get into it, starting with a problem that I think every single architect knows way too.
Does this sound familiar? I mean, come on. It's the phrase that every network architect just dreads hearing. It's that moment of pure frustration when all your dashboards are green, everything looks perfect, but your applications are completely dark. This, right here, is where the real work begins.
We're going to approach this whole thing like a detective story. A really critical connection between your clouds has failed. And the first clues you see, the VPN status, the firewall logs, they're all telling you, hey, everything is fine. But it's not. Somewhere lost in all that complexity, a single misconfiguration is just hiding in plain sight. Now, the first instinct in these situations, for almost everyone, is to just start guessing. Is it the firewall? Did somebody change a security group? This kind of panicked guesswork is what leads to those really long, painful outages. The key, the absolute key, is to replace that guesswork with a calm, methodical approach. We need a system. And here it is. This is that system. This is a powerful, repeatable mental model that you can apply to diagnose literally any multi-cloud connectivity issue. It's designed to take you from that vague symptom all the way to the root cause, step by step, without missing a thing. So, this is our roadmap out of the chaos. We always start by defining the exact symptom, not just, it's broken. Then we test for basic reachability and trace the packet's actual journey from end to end. Now, the most critical pivot, the real game changer, happens at step 4. We check routing before we ever look at security. I'm telling you, this one simple rule can save you hours of wasted effort. Only after we've confirmed the path is correct do we then go and validate security, inspect any middle boxes, things like load balancers or gateways that sit in the path, and then, only as a final step, do we look at DNS.
Okay, this slide right here highlights a distinction that trips up so many teams. You hear it all the time, but ping works? Well, that's just step 1. That's reachability. It just proves the fundamental IP path exists. Application connectivity, though, that involves DNS, specific protocols, the service itself, the whole shebang. We always solve for the fundamental path first. All right, let's put our framework into action. We've got a real-world case. An application in AWS suddenly can't reach its database over in Azure. The business is feeling it, and yeah, the clock is ticking.
So, first things first, we define the symptom precisely. The app in AWS can't connect to the Azure SQL database on port 1433. It all started after a minor network change, of course. And here's the kicker. The VPN tunnel status shows it's up, and our initial tests show a one-way failure. The connection from Azure to AWS is fine, but not the other way around.
This is a classic red herring. A one-way connection failure almost always makes people jump straight to firewalls or security group rules. They'll spend hours, just hours, digging through inbound and outbound rules, totally convinced that something is blocking the return traffic. But in our case, that is absolutely the wrong path.
Because we're following our framework, we're going to skip ahead to step 4. We force ourselves to ask this question before we get lost in a maze of security rules. Is the problem with the path the packet is trying to take, or is it with the gatekeepers along that path? This single question focuses our investigation like a laser. And this illustrates our two main suspects perfectly. On the left, you've got routing. That's the roadmap. This covers your route tables, the risk of something called asymmetric routing, and even overlapping IP address spaces, or CIDRs, that can really confuse traffic. Then on the right, you have security. These are the gatekeepers. These are the firewalls and security groups that decide if a packet is even allowed to pass. We always investigate the map before we blame the gatekeeper.
And there it is, the aha moment. By checking the route tables in Azure first, we find the problem. See, the packet from AWS makes it to the Azure database just fine. But the reply packet from that database, well, it has no specific route telling it how to get back to the AWS source IP. So it's just being sent out to the public internet instead of back through the VPN tunnel. It's a textbook case of asymmetric routing.
Now, that case study we just walked through, it's not some rare, unique thing. In fact, that exact failure pattern is one of several really common culprits. So, let's take a look at a lineup of these usual suspects so you can spot them even faster next time.
Here's a handy little quick reference guide for you. See our culprit right there?
one-way routing, and its symptom, one-way connectivity. Some other common ones are overlapping IP spaces, which cause these bizarre intermittent failures, or a NAT device that hides the true source IP, causing a firewall to just reset the connection because it doesn't recognize the return traffic. You can think of this as a criminal profile for network failures.
So here's a really crucial point. Fixing the issue is only half the battle. To really truly become an expert troubleshooter, you need to adopt certain habits. It's about moving from just technical fixes to building professional practices.
These 5 habits, they are absolutely non-negotiable for experts. Drawing the network, even on a whiteboard or a piece of paper, forces you to actually understand the path. Testing from both ends immediately exposes issues, just like the asymmetric routing we just saw. Changing one thing at a time, this is huge. It prevents you from accidentally making the problem worse. And of course, documenting the fix ensures that no one else has to solve this same mystery ever again. And this right here is the ultimate goal of the framework. You know, anyone can get lucky and stumble upon a fix. An expert can explain precisely why that fix works, what the actual root cause was, and how to prevent it from ever happening again. That's the difference between guessing and engineering.
So as we wrap this up, I'm going to leave you with this one question. After seeing this framework, I want you to think about your own debugging process. What's the one habit, the one variable you're going to change the very next time you're faced with one of these multi-cloud mysteries?